In this lecture, we'll see the notion of exponential stability of equilibrium point. Exponential stability is essentially a special case of asymptotic stability where not only it guarantees that the trajectory is going to asymptotically converge to the equilibrium point, but also talks about the rate at which that exponential rate at which the trajectory will converge towards the equilibrium point. Okay, so let's say that you have autonomous system of the form this where x of t is in D, which is a subset of Rn, and the initial condition is x0. So suppose this is what you have. Okay, now let x equal to 0 be the equilibrium point for the system. The origin is exponentially stable if the norm of x of t, okay, I should say if there exists a gamma greater than 1 and lambda greater than 0 such that norm of x of t, any norm that you can think of at any given instant of time, is less than equal to gamma e power minus lambda t, because I am considering the initial time as 0, norm of x0, if this holds. So here this lambda is essentially the exponential rate, the rate at which you will essentially converge towards the equilibrium point. If this holds for a solution when it starts from x0, then for all x0 in the region of attraction of the equilibrium point. Okay, so this we are doing for all x0 in the region of attraction of origin. Okay, so now how can we verify this? Because we already have the idea of Lyapunov theorem. How can we verify this from the Lyapunov theorem, or what modification will we do? So consider the system this with x of t being in the domain D, that is a subset of Rn. Let V that maps from D to R be a continuously differentiable function such that v of 0 is 0, v of x is greater than 0 for all x in the set D excluding 0. V dot of 0 is 0 and v dot of x is less than 0 for all x in this. In addition to this, alpha's norm of x should be less than equal to v of x, which is less than equal to some beta norm of x, and v dot of x is less than equal to minus gamma norm of x. Okay, please note that the order of the norms in this case will be the same, with alpha, beta, gamma, all of them being greater than 0. Okay, so let v be a continuously differentiable function such that it is positive definite, v dot is negative definite, and you can find a upper bound on lower bound on v in terms of norm of x and a upper bound on v dot in terms of norm of x. Suppose you can do this. Then the origin is exponentially stable. So the positive definiteness of V and negative definiteness of V dot ensure asymptotic stability, because as t approaches infinity, it will go towards the origin. Now the other two also, I mean, these conditions that you see here also ensure positive definiteness of V. Okay, because V can the norms cannot become negative, and the lower bound itself is positive. Okay, so that is why you have this holding, and v dot has to be less than equal to minus gamma norm of x, so v dot has to be negative again, negative definite. So these two conditions themselves actually represent the first two conditions that we have written. So for exponential stability, what you need is v has to be a positive definite function so that it is upper and lower bounded by some norm, some scale norm of x, and v dot is upper bounded by some scale norm of x, negative of scale norm of x. If this is true, then the origin will be exponentially stable. Now if you want this to be globally exponentially stable, okay, then what you have to add is origin is a unique equilibrium point, and d is Rn. You notice here I am not explicitly writing that v has to be radially unbounded. Why? Because v is upper bounded by uh, some scaled version of the norm of x, and the norms are always radially unbounded. Okay, in fact you notice v is lower bounded also by a norm of x. So the norm of x is radially unbounded. So if the lower bound is radially unbounded, then v has to be radially unbounded. So that is inherently there in the exponential stability condition. Okay, so radial unboundedness of v is captured by the lower bound alpha norm of x that we have. Now one thing that you should actually Okay. Yeah, so the lower bound captures the radial unboundedness of Vx. So that is why I have not explicitly stated that V has to be radially unbounded. If we need exponential stability because of these conditions, V has to be will be automatically radially unbounded. Just that we need the entire domain to be Rn and origin to be a unique equilibrium point. Okay. Uh, okay. So one thing that you should notice here again is the following. Because of the conditions that we have for v and v dot in terms of the norms, and please note that these norms can be the same. For example, sorry, this is not just norms, this is not just norms, this is norm squares. Sorry, the norm squares, not norms but norm squares. Now these, for example, you can consider them to be two norms. So what you have here is the Lyapunov function v and the Lyapunov function v dot are of the same order. Okay, so this is something that is necessary for establishing exponential stability using Lyapunov theorem. Okay, please note that when I stated the theorem, I had missed a square over the norm, so please ensure that you have the squares over the norms. Okay, so you can just correct that. Okay, so what we have seen throughout these lectures are, I mean, when we started stability, we saw the notion of stability in the sense of Lyapunov. So basically, the epsilon delta ball definition that we had. Then we saw the Lyapunov theorem for stability and asymptotic stability. This is also known as Lyapunov's direct theorem. Then we saw the region of attraction that we can get, an estimate of the region of attraction. Then we saw how can we use what is the modification that we need to do so as to establish global asymptotic stability. So as to establish global asymptotic stability. Then we saw the idea of exponential stability and global exponential stability. Okay, so we have seen this, which and we saw that how GS, ES, and GS can be established using some variation in the Lyapunov direct theorem. Okay, or the Lyapunov direct method. Lyapunov direct method is also something known as a Lyapunov's indirect method. Lyapunov's indirect method, and this method essentially involves the idea of linearization that we had seen. Okay, um, so consider the autonomous system that we have. Consider the system x dot of t is f of x of t with f being a map from D to R, D being a subset of Rn. Let x star be a equilibrium point of the system, let A equal to del f by del x evaluated at x equal to x star. Okay, so this is how we used to form the Jacobian. Okay, so A here is the Jacobian matrix that we have. I forgot to add that f is continuously differentiable. Okay, because you're differentiating with respect to x, right? It has to be continuously differentiable with respect to x. And this d here is some neighborhood of this equilibrium point x star. Then x star is asymptotically stable if real part of all the eigenvalues of A is negative. Okay, so lambda I is the ith eigenvalue of A, and the real part of all eigenvalues of A has to be negative. That is the case, then x star is asymptotically stable, and x star is unstable if real part of eigenvalue of A is greater than 0 for one or more of eigenvalue of A. So at least for one eigenvalue of the real part is positive, then the equilibrium point is unstable, and we had already seen this in some form in the previous lectures. Okay, so we'll stop here, and in the next lectures we'll discuss examples that encapsulates all the ideas of stability that we have seen here. Okay, so thank you.